so she can. Okay. All right, so let me stand here. Okay, so hello everyone. Thank you for making to today's talk. I'm so excited to see this many people show up in person, interact with me. Also, thank you for the people on the Zoom. I think today you see the weather is raining, but just thank you for showing up. Isn't that a great time to discuss research ideas in this chilly afternoon? So basically, I'm myself very excited about this topic and today's talk. It's probably not going to be as impressive as Song Yang's talk, like Zijie mentioned, but I will try my best. I hope you enjoy it. And if you want to follow along, I just send the link of the updated slides in the channel. It's the same link, it's just I made some more updates this morning, so you can download it. But I think you should enjoy it more if you follow my pace. So for today's talk, some of the slides I adapted from Kevin and David, just for their credit. What I will be talking about today is this explain AI models by locating and editing knowledge. So the outline will be like this. I will first give some background knowledge about explain AI models and locating and editing knowledge. Then we will look into these 3 papers from past NeurIPS and iClear. 2 of those are spotlight papers. At the end, I will talk about some future directions because this is really hot and like new research direction right now. There are so many open problems. I'm just dropping out some ideas, but more discussions are definitely welcome. So let's start about the background. I will start by talking this big picture of the AI advancement in the past maybe decade. So we see the AI models have achieved remarkable results, right? They achieved remarkable results in many different domains. Sometimes they can outperform humans, and sometimes they can help make new breakthroughs. For example, if you think about the vision task, for this deep face model proposed in 2014 has already achieved human level performance for face recognition, which is 97.35% accuracy. That's already 10 years ago. And for the language models, right? So there used to be this very strong benchmark super glue combining 8 different challenging tasks. But by 2021, you also have models that can outperform human level performance on this super hard benchmark. Right, for graphs that we are more familiar with, we see GNNs has been used. Maybe one need to mention breakthrough is this development of halicin, which is a chemical compound in 2020. This is the first new broad spectrum antibiotic ever discovered in the past 30 years. Right, this is by James Collins, Tommy Jacola, and Regina Barsley from MIT. So now to mention the generative models, right? We have ChatGPT, DALL-E, and all of this, right? So I think you are all familiar with this. But behind all of this advancement, there is this question that's not, at least not perfectly addressed now, right? It's why these models works. So from 10 years ago, we see these models making great breakthroughs, but we still don't have a fully understanding of how did they get there. This to me is a very important problem. It bothers me, so I think about it day and night. I hope through today's discussion, I will convince you this is also an important problem, and maybe you will get interested in working on some directions for better answer this question. So this why question I showed on the previous page, right, is actually a very, very open question. To now, it's not really well defined. But let's first talk about why this is important. Why do we want to solve this question? There are many arguments you can say from different literatures and different researchers trying to provide their perspectives. But in summary, there are the following few points to emphasize the importance of this question. The first thing is that if you can better answer this question, you will be able to improve your model performance, right? A direct example is that whatever objective you define for your model, for classification and maybe cross-entropy loss or whatever, if you are able to better explain what's happening within the model, then in principle, you should be able to make a way to have your model better fulfill this objective. What's broader than that is this alignment problem, which recently has become the hot topic. If you think about it, better understanding why a model is doing something to explain the mechanisms of the model can help you to achieve better alignment. There are other ways to achieve better alignment. Maybe people do RLHF. But to me, this answer this why question is a shortcut, and it's one more principled way to get better alignment. Another perspective we can argue is that this improves human-model interaction. So for example, if you have some users want to use your AI model, but have no background knowledge about like machine learning or anything, then providing a better answer to this why question can still improve their trust and satisfaction, right? In some cases, like face recognition is probably not that significant, but if you think about the like doctors using models to make medical decisions, they definitely want to know more about why the model is making these kind of suggestions. Another thing is that we see that right now a lot of decision making, and especially something the model cannot do, we need to have human in the loop, right? I know many of us are working on the GPT reasoning ability and hallucination of large language model, this stuff. We do see there are these shortcomings of AI models. So at least for now, the best and the most promising way to me is to bring the human knowledge and the model knowledge together to achieve something. But in order for these two modalities to work together organically, you want to have a better model understanding to get there. So as I mentioned, this question is still very open. We discussed why it is important, but what are some possible answers we can provide for this question, right? I also summarized in 3 bullet points. These bullet points, there is no like super clear boundaries between them, and you may be able to come up with more ways to answer the question. But let me just tell you about my categorization of the answers. The first thing is that you can provide an explanation of the model mechanism, right? Some more concrete example will be like, I can give an analytic expression even if the model is very simple. For example, if your model is as simple as fx equals 2x plus 3, then I can just write out this expression 2x plus 3. Then that's a perfect explanation, because I'm telling you, no matter what kind of input you give me, I will multiply it by 2 and plus 3 to it, right? Unfortunately, in real life, the useful models are not that simple. But there is one category of models, people call it inherently explainable model. For example, the linear regression model. It's much more complicated than 2x plus 3, but still you can just look at the linear coefficients to figure out, oh, which feature is more important and which feature is contributing positively or negatively for your final prediction, right? Another example is that people do this kind of layer visualizations. This is back to 2014. Where they try to study CNNs by visualizing all the filter matrix to see what do this matrix capture, right? So all of these 3 examples, they are trying to convince people, okay, this is the underlying mechanism of the model. I'm trying to tell you what the model is doing, but so far we don't have a perfect solution for those very large models. A second perspective is try to look at, like here, I want to emphasize one. Look at one data point, look at how that is processed by your model, right? Examples are like, you can highlight key parts of that data instance. Might be some objects in the image, words in the sentence, or subgraphs in the graph. Or you can even argue the attention mechanism is also trying to show which word is more important for producing some semantic meaning. Here, I'm showing one example from 2020, the work called GraphCam, where the original image was one dog and cat. But when you try to predict whether there's a cat in the image, you can produce this kind of heat map to highlight the areas correspond to the cat, right? This is the second way to show the explanation. But there are actually, like I mentioned, no clear boundary between these two, because you can imagine when you try to explain a mechanism, you can explain it maybe by providing a bunch of examples. Or after you examine many examples, maybe you can summarize them together to reflect something that's true for the model level explanation. But given both of this, I think another example worth mentioning is that you really need to focus on this human understanding, right? So basically, you want your explanation to be personalized, or in other words, for your listeners to understand what you are talking about. Right? For us, for example, if we just show attention for some model, maybe it's good enough. But if you look at this question here, like explain moon landing to a 6-year-old, if you talk about attention heat map stuff, doesn't make much sense to the 6-year-old. So in this case, we are kind of trying to find a balance between showing what's going on for the model and the data to how can I have my listeners better understand me. So this has been a question. I think all the researchers in this domain try to find that balance. So, okay, that's pretty much the background of model explanation and some of my personal views. For today, we're going to look at this specific way of answering that why question through explanation, basically locating and editing knowledge. So you can think of this as somewhere between the first and the second bullet point in the previous page, where you try to examine a bunch of examples and finally make these observations to come up with some model level conclusion. Maybe to motivate you a little bit more, I want to mention a quick background story of the author, the primary author of the first two papers here, David Ball. David himself, he graduated in the 90s with his master's degree from Cornell, and then he worked in Microsoft and Google for 20 years. So then in his 40s, he decided to go back to academia, so he started his PhD. So right now, I think he's in his 50s, but he just started as an assistant professor in Northeastern University for 2 years. So you can imagine, at least for me, for this kind of researcher, for them, the primary goal is definitely to make impactful research, right? I don't think there's much financial consideration or like publishing cheap papers or things like that. So I would really encourage you to maybe study some of his papers. Like, for example, the representative one is the first one. I think it's really visionary and also really dense. He tried to tell a lot of things within one paper. Okay, so again, let me try to state some general things about locating and editing knowledge, and then we will get to these three papers. These three papers, you can tell from the title, they are focusing on GPT and transformer and language model. But I would say the general technique here should be able to apply to many other models as well, because David himself, he was working on explaining the GAN model for image generation. And I think he is a close friend with Boley from our department. They collaborated on many like computer vision model explanation papers. So, okay, so again, let's get into the sub-direction of model explanation by looking into the GPT model specifically. So we ask this question to start. What does GPT know? So for this example here, assume we have a factual tuple with a subject, a relation, and an object. It can be this one, like Edmund Neupert. If you don't know him, he's like a famous pianist. And the relation can be placed the instrument and the object will be piano. If I ask this question for GPT, I just input Edmund Neupert, comma, performing on Z, then GPT will be able to finish the sentence with piano. And I can ask the same question for many other musicians, for example, Miles Davis and Nico Paganini. But just with this GPT-2XL model, it can predict the correct instrument played by these musicians. So in this case,
I just want to confirm.
Yeah.
Input is like the subject, comma, relation. That's it.
No, input is exactly the black text here. So here we're trying to show, trying to show two things. One is that when we get this tuple, we imagine it as a fact in its raw format, right? Mm-hmm. Here you can imagine this is like a prompt, maybe. So for example, Niccolo Paganini is known as the master of Z. Until there, that's what we put into the model.
Of Z, okay.
Yeah,
that's the prompt.
So this whole part is also the input. Mm-hmm. So why we want to emphasize the difference is that for the relation, For all four musicians, the relation will be place the instrument. But when you describe this relation, you can use different wordings. That's why we are saying, later on we will see this is like an important difference between these two, because we try to have the model to perform consistently, even though when we rephrase the relation using different words, right? So we will call this a tuple or call this a relation, and we'll call this a prompt. Okay. So people wonder why GPT can correctly, first of all, correctly predict the instrument of each musician. Second of all, not mess up with different musicians, map them to the wrong instrument. And then so we try to figure out how did GPT know this, right? If you look at how we get the GPT, we first collect a bunch of data, maybe a corpus with billions of words. Then you put them into this transform model and train it autoregressively. And boom, you get a black box GPT model that can do the amazing things on the previous page. So how did that happen? If we zoom in and take a closer look, right, here with another example saying the Space Needle is in downtown, this black box will output Seattle. This is the correct answer, but what happened in there, right? It's actually just a bunch of layers, with each layer having these hidden states in purple and some attention computations in red and some MLP layers in green. So it's saying that with a bunch of math in between those learned parameters, you will be able to figure out the correct prediction of the Space Needle is in Seattle. So we really need to understand what's happening for this colorful bunch of parameters. So this connects to two ideas from machine learning, overfitting and memorization, right? So overfitting, I guess I don't need to speak too much about it. We all know that large language models can easily overfit the training data as long as your model is large enough. When I started learning machine learning, this is kind of a very negative word, but I guess recently it became more and more like a neutral word. People even come up with ideas like a benign overfitting. So because in the past, it's kind of the opposite to generalization, but right now people are saying that the large models can achieve both overfitting and generalization at the same time. A very similar idea is this memorization, right? So actually, even back to 2015, people started looking into so-called the memory networks, where they try to build a very large network to memorize a lot of stuff. And then when they have new things, new data points comes in, they just try to extract something from the already memorized data and then to answer the new questions. And then more recently, in 2020, people shown that transformer layers can work as these key value memories. This paper here will be an important prerequisite for what I'm presenting today. So this makes us making this hypothesis saying that neural networks, especially the GPTs or large language models, they are able to memorize facts. Right? And then based on this hypothesis, the papers I'm going to present today, they make this approach of studying large language models as neuroscience problems, right? Because memory itself, for neuroscientists, they study it for human brain, although I don't think they have completely figured it out, but it's very important research topics to study for human brains. Right now, we are trying to make this connection. So we first ask, how do GPTs compare to an adult human brain, right? So according to the third paper listed below, there are approximately 86 billion neurons, which is the GPT-3 level of an adult human brain. And there are like 100 trillion synapses.
So, wait a second.
Yeah.
For neurons, they're just the nodes. So when I say they are at the GPT-3 level, but GPT-3 like 175 billion, that's the weight. Weight is the connection. Among those 86 billion neurons, right? So you can imagine that the connection definitely could be potentially quadratic.
Right, so that's why I think this is referring to the connection 100 trillion.
Yeah, then why do you say that's the GPT-3?
Oh, this is, I think even for the human neuron and the model neuron, they have different definitions, right? So here it's just trying to say the number itself is like,
but again, it's not comparable because for GPT-3, when we say 175 billion, that's about the connections, that's about the weights. So that's why we shouldn't equate these two.
Okay, I see. Yeah. So if we want to connect to really to the connections, maybe you should compare to this number here, 100 trillion.
Right.
So in this case, we are like a few magnitudes below.
Yeah, but of course, GPT-4 rumor says already 1 trillion, and I think the more latest version, I don't know what's their
I see.
latest version.
Yeah.
Definitely it's gonna be even bigger.
Yeah, I think the argument this paper are trying to make is that right now the model is maybe not exactly the same magnitude, but it's large enough for us to treat it as if it's a human brain. Maybe not a human brain, but some mammal's brain, yeah, to study it. So if we choose to study it this way, like very brief summarization of how neuroscientists are doing their work is that they apply stimulus to the human brain and collect some activities and do analysis. Right? From this perspective, studying the neural network models with kind of this method is actually an advantage because you cannot do anything you like to a human brain, right? It's not easy to open a human's head and collect all the signals, but you can do whatever you like for a large language model as long as you code it right. So in this case, we will see for the 3 papers I'm going to talk about, they apply different stimulus to the language model, they collect the activities and they do the analysis. Right? Okay. So this brings us to the first paper published in Europe's 2022. Here, David Bowe is the author. I used that motivation example. The paper is called Locating and Editing Factual Associations in GPT. So the paper is exactly trying to answer the question I presented in the previous slides, seeing where and how are facts stored in GPT. They answer this question in 3 steps. The first step is that they try to locate where the fact is by doing something called causal tracing. The second step is that once they figure out where is the fact, they try to edit it by using something called the rank 1 model editing, ROM. The third way is that they propose their own data set to measure the edit success. So throughout today's presentation, I will always first present the main idea of each paper, and then we will look into the mathematical formulation to see some formulas. So yeah, I hope you get a better understanding of things by first seeing the idea and then seeing the formula. And also, if you have any questions, just feel free to interrupt.
Before that, I really want to understand what are facts. What's the basic form of facts? So in the earlier slide, you gave example, it's a triple. But actually fact could be more complicated than that.
Yes.
For example, subject, attribute value. So it's kind of unary relation. And what you have shown is like binary relation. We can also have like a multi-relational fact, right?
That's definitely one future work. I think I also listed it in the last.
But
for all 3 papers, it's just the subject relation object.
I see.
Yeah. Thank you for the question. Okay. We will start with the first question, how to locate the fact with causal tracing. So this causal tracing is actually a simple idea. I think the challenge part is that how to correctly code it. So the idea is to apply interventions to trace the information flow in GPT in 3 runs. So we call it a clean run, a corrupted run, and a corrupted with restoration run. So for the first run, the clean run, you will predict some fact, just as the example I showed at the beginning, just to do a regular GPT forward pass. The second step, you will corrupt your input such that your prediction is damaged. You get something like that doesn't make sense. The third step, you will try to restore some part you corrupted to see whether that can recover the correct behavior of the GPT from the first run. Right, that's the general idea here. So picture-wise, let's look at this same example. The Space Needle is in downtown Seattle. So the clean run is just very straightforward. You tokenize your input, put it into GPT, and then output will be Seattle. For the corrupted run, you make some changes. In this case, you add a noise to the first 4 tokens. By adding noise, I'm not saying adding some small noise, but in this case, you actually add a large noise such that these 4 tokens are not distinguishable from the random noise tokens. Sorry, their embeddings are not distinguishable from random noise embeddings. So in this case, you can imagine you completely destroy the information comes in from the first 4 tokens. You are basically just asking noise is in downtown and see what GPT can output. Right? Turns out in this case, most likely GPT will output something like doesn't make much sense instead of Seattle. So what's happening is the third step. So you just did the first one on the left and the second one on the right. What you can do is that you collect all the hidden states you got from the first one, and you copy the exact parameters in one hidden state, and you put it in your corrupted run. Okay, let me say more detail about it. So you can imagine you had maybe like 2 models. Right? So the first model, you just do the regular clean run and you keep it there. The second model, you do the corrupted run and you keep it there. But you want to test it recovering which part will help the corrupted run to behave normally. So you collect one hidden state from the first model, and you just force rewriting the hidden state here, right? And in the paper, the authors actually did that for many different states. What they want to say is that whether I can, by doing this patch, to recover the Seattle output for the corrupted run, right? So here is another example, which is shorter, so we can put it in the same page. It's Miles Davis plays the trumpet, right? You can see in the corrupted run, I put all this attentions and MOP and hidden states in different colors. So once we copy over this hidden state here, everything in yellow will still be affected by the noise, right? Basically towards its left and up. But everything towards its right and lower, this part, they will be affected both by the noise and the copied state, right? So I also have this, the authors, they had this animation here to show you what they actually did, because they did it for all possible hidden states, right? It's a corrupted run, and they try to copy over for each hidden state to test what's happening. And by there, they hit one correct output CBS. But for many other hidden states, it's still unreasonable output until here, they hit the correct output again. Okay, does the idea make sense?
Okay, but so from efficiency perspective, you mentioned they are going to replace all the possible hidden states.
Right. So here they actually did the experiment for a GPT-2 XL model, which has 48 layers, and then the token length, it depends on what's your input. So if you input T tokens, it will be T by 48. Yeah.
What's the number of layers in like
48.
GPT-3 or like Llama 2?
Actually, I'm not sure, probably like 70-ish. Yeah.
Token size like 1,000.
Token size, it depends. So if your fact is just a subject relation, it won't be very long, because you say you like in this case your token size is just a 4. So you input the subject and the relation, then that's it.
So the inputs, do they have like some knowledge graph? So they just test each of those facts from that knowledge graph?
You can think of it as a knowledge graph, but they collect it just as a bunch of tuples. Yeah.
How do you correct in that practice?
So just imagine you have 2 models, right? The model architecture are exactly the same. So the first model, you do the clean run and then you record all the embedding. Like you just store it somewhere in your memory. And then for your second run, you just grab the embedding from the same place and replace it when your forward pass get there. Yeah.
Oh, I mean that the input, like the
Corruption. I think it's random.
random corruption.
Or corruption, just add noise. So you have another Gaussian random variable, which has really large variance. And then if you add that variable to the input, basically this will become like a very flat. So imagine your original embedding is a distribution, some semantically meaningful distribution, right? If you add a Gaussian noise to it, you will destroy that semantic meaning. Yeah.
Can I have a quick question? Sorry, I might miss it. For the blue circle, because like the purple circle means like the original hidden state, and what's does the blue circle mean for the second figure? So we have the yellow one, which is corrupted, and then we have the purple one, which is the original one, and then for the blue one, it is like,
Yeah, this is a great question. So imagine in the clean run, everything is purple, right? So if you just corrupt it, everything should be yellow. But once you copy this purple one and you look at the one next to it, it will be influenced by both the copied one and some corrupted one, right? So for example, this one in the second row, column 3, is not the same as this one in second row, column 3, because this one is influenced by both this yellow one and this purple one. Can you see?
oh, okay, thank you.
Probably
Oh,
not.
I can't see like your.
I was talking about this one is influenced by both this purple one and this yellow one. Yeah.
Oh, okay, thank you.
So because for the attention computation, right, you look at all the things from the previously.
Thank you so much.
Okay, so I think maybe after seeing some formulas, this will become even more clear. So let's try to formalize what we just talked about in the examples, right? So the first thing is that we need to review how transformers work, which is this figure on the left, right? For the clean run, this is the goal. We want to output a T by L matrix storing these hidden states, right? T is the token size, L is number of layers. And what you get is that you first start from your input X, and then you get the embedding. This X is one token, and you get the positional encoding, and then you get the initial hidden state, which is this area, right? After that, you will do two addition, like through the residual connection. One is collecting the attention term, one is collecting the MLP term. The MLP here is called feed forward. So, but basically what is happening is that, oh, I compute attention from all the L-1 layers, I get this A. And for the MLP, it's like I put the attention and the L-1 layer together, go through this gamma, which is normalization, right? Which is normalization. And then I go to a fully connected layer. And then this sigma is the activation function, and I do a projection. Well, the formula maybe like look a bit complicated, but this is just two-layer MLP. Shouldn't be very hard to understand. Because here you see, once you get H0, you will go through one step of attention, add it, and go through one step of MLP, add it, and output it, right? So I guess you should be familiar with this transformer setup. And for the corrupted run, similarly, I want to get an output with H, but here we also add this star next to it to indicate it's corrupted. It will be exactly the same size as the clean run, but the difference is that at the 0th step, you add this noise epsilon to it. So you destroy the semantic meaning. And finally, when we say restoration, mathematically, we're just saying, well, we replace the corrupted HIL with the correct HIL. Okay, I hope this makes sense. So then let's look at a concrete example with an input fact. So imagine we have this knowledge tuple S, R, and O. Then I will have a prompt. This is related to Izhou's question in the beginning. I will call this a prompt, but this prompt actually just describes the S and R. Maybe the R is place instrument, but the X can tweak that relation in different ways. Right? And finally, I will input my prompt into the model. For the clean run, I get regular H. For the corrupted run, I get H with the star. And finally, I will be able to have 3 outputs. The probability of outputting the correct object O here, the probability of outputting O in the corrupted run, and the probability of outputting O in the restored run. So these are the 3 values I want to compare to test my understanding of the model. And this is what's so-called causal tracing. So let's see what we actually get. The metric used in this paper, they call it indirect effect. Basically, it just takes the difference with the restored version versus the corrupted version. If we look at the difference, you can actually create a heat map like this. So again, you have this T by L matrix. What the author did is that for each IL entry, right? They copy over the hidden state. So in principle, you will be able to get a matrix with T by L. And then if you look at the matrix, the majority of the matrix, they are just to give you some value really close to zero. I think that makes a lot of sense because you only recovered one hidden state in, let's say, 7 by 48, right? You have 7 tokens. You only recovered one hidden state for 7 by 48 matrix. Most likely, it won't help you much to gain the semantic meaning you destroyed through adding noise, right? But what's interesting is that there are 2 areas in this matrix. When you add back the clean output, the clean hidden state, you do get the correct behavior of the GPT. So the value can be as high as, like, say, above 0.8. So in other words, that's like saying, it doesn't matter that I destroyed the input subject here. As long as I have this hidden state correct, then I will be able to predict Seattle from this hidden state. So if you think about it, why this is possible, right? So there are 2 areas. The second area actually makes a lot of sense. Because when we do this language model next token prediction, what you do is you just take the last token from your input and you predict the next token from here. So if you recover the last token here, it actually doesn't matter what you did for the input noise, right? It will be the same as the clean run. And for this state a little bit towards the left, it's just saying, oh, they are too similar to the very last token. And at the very end, your model didn't do much. So as long as you recover this part, you will also be able to predict Seattle.
So I need some time to understand the heat map.
Mhm.
So first of all, to generate the heat map, we need many corruption, right? And
No, you only need 1 corruption, but you need many restoration.
we only need 1 corruption, but many restoration. Okay, so here, so each time you corrupt, how many words? 1 single token or multiple words?
Oh, yeah, that's a good question. I need to mention, in this case, they only corrupt the subject.
Okay,
Yeah.
they corrupt the subject and then they can based on like number of token times number of hidden
Number of layers.
Yeah,
Yeah.
so that many possible wrong. And based on that, you can calculate what? The difference between the output and the
Yes.
ground truth?
Not the ground truth, but the result from the corrupted run. So let's see.
Mm.
For what's on the left, you do it once. For what's on the right, you do it once.
Mm.
But you copy over each hidden state. So for the third step, the restoration, you do it T by L times.
So
Right.
that heat map is just like, if that replacement was a huge difference, then we will have like high value.
Yes.
On that, okay.
So that heat map is just this formula. So this is the corrupted run, your second run, the output of the Seattle, the probability of Seattle. This is, you will have T by L many of this. Each of them correspond to restore 1 hidden state.
So for metric wise, it's just like measure the difference of the probabilities
Yes,
in terms of the ground truth.
yes, O is the ground truth. So you are giving, so you can imagine you have an input tuple, right? The subject is the space needle. The relation is probably like located, right? And here we rewrite it as is in downtown. And the output is Seattle. You know this for a fact. And in the clean run, GPT is able to correctly predict it.
Mhm.
In the corrupted run, GPT fails to predict it. And then you tested T by L many restorations. Some of them will be able to predict Seattle, some of them will fail.
Yeah, most of those places, actually, they are 0, meaning
Yes.
that they will not really affect the
They won't.
output.
Yeah. Because imagine you have T by L number of places, right? And many of them are like influenced by this input noise. Here, you just try to restore 1 place to see whether you can recover what's what's damaged by the noise. So in principle, you should believe everything is white. But it just happens that for some of these states, as long as you recover it, they turn yellow, they turn purple.
Does that imply those tokens actually is more important?
That's the juicy part of the paper. We'll discuss more later. Yeah. Okay, any other questions for this part? Yes.
I'm wondering, like, I read the original paper and it says, like even with the corrupted input, it was able to alter probability for the correct target that is like 3 times lower than the probability of using the correct input. So I was wondering, like, why didn't they just use like a random input vector instead of adding inputs to the.
I think that's probably just more for convenience. I'm not entirely sure. I actually had the same question, but I agree that if you just input the exact same, like just input exact noise instead of adding noise, you should be able to achieve similar effects. But I think what they have in mind is that they try to put everything as in this framework. So they try to think of everything as residual. This will probably become even clearer when we get to the second paper. So originally you have H. Along the way, you just add a bunch of attention and MLP output to it, right? So the difference here will be at the first step, you add about a bunch of noise. So you can think of everything as just you keep adding up things to your original H. Think of it as a residual. Yeah. Okay, any other questions? So if no, let's continue. So what's on the left is just for one example, the Space Needle is in downtown Seattle. But what's on the right is that they did the same thing and they averaged it over 1,000 prompts. And they also observe a similar effect, right? So here we look at the x-axis is the same, it's just 48 layers. If we look at the y-axis, it's changed a little bit, right? Because for different prompts, you may have different lenses and you may have like a different subject and relation descriptions. So they summarize things into this, right? You have your first subject token, middle subject token, last subject token. And then you have the first token after your subject, some future tokens, and the last token, right? So after the summarization, what they conclude is that, well, the important or the interesting things always happen at the last subject token. So that's like saying you can have many different ways to frame your prompt, but you really need to pay attention right after you state the subject. That's the critical part, right? And that holds true for 1,000 input prompts. So they also did some like more fine-grained analysis. So here we are copying over the hidden states, the purple part, but you can also choose to copy over the MLP parameters or the attention layer parameters, right? For this tool, what the authors found was that if you only copy that for one layer, you won't get much. Basically, you will get like a white matrix that's not very informative. So you really need to copy over 10 layers, right? So here, what this is saying is that if we are looking at position 10, you actually copied over all layers from 5 to 15. And then you can observe this similar pattern with the last subject token provide a lot of information. Okay, that's the first part of this paper. They did so-called causal tracing and they observed this special last subject token and that early state. The second step is to further verify this finding by editing it. They call it rank 1 model editing. So to do that, we will also look ahead back to this 2020 paper, where this paper discusses that the associative memory view of an MLP layer, right? So this is the MLP formula I just copied from the previous slides. So if we look at it visually, it's something like this. Well, at the beginning, you do some fully connect layer, you do this activation, right? Like regular things. What's interesting is this very last step of doing the project map, right? If you imagine the output of your first fully connected activation as the key, and then you imagine the output of this final output of MLP as a value, you can view this projection layer in the middle as a key value memory. This is, of course, there are like a very detailed discussion and experiments in this paper talking about why this is a reasonable thing to do. But the effect is that we assume through this projection layer, we will be able to map a representation of the Space Needle to a representation of Seattle. Or similarly, you can map the representation of Atom at Newport to the representation of Place the Piano. That's like the hypothesis that we can get from this paper.
But if it's just the MLP, then we can differently consider the mapping. But now this MLP is after the attention layers.
Right.
And it's done like individually, right? So after this attention layer, after we get this latent state for each token, we just do the MLP independently.
So what do you mean by independent?
Or they has to be concatenated together to do the MLP. Because I try to understand the
they have,
projection.
yeah. Are you saying this step of this is attention, this is hidden? Are you saying they have to be put together to go through the MLP?
So we have multiple tokens, right?
Yeah.
Then afterwards,
Oh,
For each
for
token.
multiple, no. This is just looking at the one token.
yeah.
Yeah.
So for each token, we're going to do the projection, the MLP.
Yeah.
Previously, when we do knowledge graph embedding,
Mhm.
when we do the projection, we know which relation we're going to apply. For example, UCLA is located in LA, right?
Mhm.
Then UCLA is a subject, which is like represented as like representation vector. And we know that now we're going to apply is located in. So then we just read out the corresponding MLP or whatever transformation. Then we're going to transfer it into the object entity. But right now, this projection, like, I don't know where I'm leading to, because like token by token, for each specific token, I'm going to do some transformation. But now you try to link that kind of transformation to certain projection, which to me is like we did design that, right? But why you make the conclusion that, okay, this projection actually is related to some certain relation?
So here is not, first of all, I don't think this is about the relation.
Okay.
This is just saying that if you have some weight matrix, right? And then you input a vector to this weight matrix, project it to another vector, right?
Yes.
We can imagine the input as a key, the output as a value, and this weight matrix as a memory of storing this relation. This is all this page is saying.
Yeah. But this projection is applied to each single token.
Yeah, so how about we look at this page?
Mhm.
So here we have 4 tokens, the Space Needle, right? And then once we get to this MLP, through the attention computation, this hidden state already contain information for all first 4 tokens, right? Do you agree?
Yeah.
Then we can see that this hidden state somehow represent a key value corresponding to these 4 tokens. When it input to this MLP here, we'll be able to extract the value, say maybe like in downtown Seattle. Yeah. So yeah, so if we zoom in a little bit, this is exactly what the hypothesis is saying, is that for this particular MLP, when we input Space Needle, we will be able to output located in Seattle, right? So for this visualization, we pick the MLP at the end of the subject token and to some early layers, right? So that's corresponding to the heat map conclusion from several slides ago. And then the question we ask is that, well, in this case, assume the hypothesis is true, that we do have the information stored in this MLP. Can we change it? Right. So that's one way to verify whether you discovered the correct thing, right? So if you are able to, let's see, here it says Seattle, and that's the correct output. If you are able to do something just to this MLP to change the output to Paris, then that means this MLP stores critical information, right? So here, when we're talking about this editing, everything else, like all of this colored stuff besides this MLP are kept the same. right? So it's a clean run. Right now, there's no noise anymore, right? I want to emphasize it. It's a clean run. The Space Needle is in downtown. And I picked out one single MLP from my clean run, and I try to do something about it such that the output is no longer Seattle, but Paris. Okay. So, yes.
Question, so I just want to confirm it's like causal language modeling in the sense that like the direct attention only to tokens before, right?
Yes. Yeah. So whether it's causal or not, I think it's debatable. In the paper, they try to promote this idea and citing some Yuda Pro's paper. But I think to causal researchers probably not. Yeah.
Absolutely causal, but
Yeah.
that's the word they use, right?
Yeah, but they do only consider like this time constraint. You only look at the previous token.
That's the case for all the decoder only.
Yes, that's yeah. In this case, it's very specific. It's just the GPT-2 XL, right? So whether this can be extended to encoder-decoder model, we are not sure from these papers. So again, now let's formalize it a little bit. So the p-value store idea we talked about, I told you that's from a 2020 paper, right? Actually, it can even date back to the 1970s. So in the 70s, people already know that if you want to store some key value vectors, right, listed in columns of these two matrices, then you can store them using a pre-trained weight matrix. Or maybe not pre-trained, you can store it using some weight matrices. And in this case, if we look at the pre-trained weight matrix in your language model, then they should satisfy this least square constraint. All of this is conclusion from these 1970 papers, but if you think about it, it's very intuitive. If you want this weight matrix to map each k you care about to the corresponding v, that's like asking it to solve this least square problem, right? So I think this is a very simple idea, just formalized in this p-value store statement. And the solution is just the normal equation from your linear regression class. You should be familiar with it. Maybe when you saw it, it was a format like this. I just put here for reference. But in this case, it will be something like that, because for these two papers, they put the key value as columns instead of rows. So your k here is the transpose of x, right? But you should recognize this is just a normal equation because you can take transpose on the left, transpose on the right. You get back what's sitting here. Okay. And then for the ROM of inputting, do that editing to input the new knowledge, it's just saying that now we have this new k and v, not included in my k and v matrix. I want to include this piece of information also into my weight w, right? So in this case, you're just saying that I want to minimize I want to solve a new optimization problem. The objective itself is the same, but now I have a constraint saying that I should map this k star to v star. That's what I want to edit, what I want to insert to my weight matrix. Just to remind you again, here we have no noise anymore. The star used to represent the noise, right? When we were talking about causal tracing, but now we're talking about editing. Star is just used to represent something new, something different from what you already have. And then turns out for this constrained least square problem, you can actually also solve it explicitly, right? What you will get is that, well, you will get this formula, and then with lambda matrix equals this, C matrix equals this. So the derivation is kind of long, so you can read it in the paper. What I'm showing you here is just that there is a closed form solution for inserting the new k and v. And then this ends up showing us rank 1 update. So what do I mean by rank 1 update? So if we compare these two things, right? The W0 is everything before edit. The pre-trained model have an MLP with this parameter. But now you want to insert a new k star into it such that W1 will output V star for you. Then if you compare these two cases, they all have explicit solution forms. And then this just tells you W1 just equals W0 plus this extra term in the red box, right? You see if you multiply k transpose inverse on both sides, and then you will get this term, plug it in, this is what you get, right? So on the left is saying that if you want to get both of them, what should you do? On the right is saying that if you want to get W1, what should you do about W0? So it turns out this thing in the red box is just a rank 1 matrix because both lambda and the C inverse K star are just the vectors. So for inserting this K star into your weight matrices, you will just do a rank 1 update of the matrix, and then now you will be able to get out V star. Okay, so I want to confirm everything makes sense. Yes.
The reason that it's a rank 1 matrix is just because the solution to a problem leads to a rank 1 matrix.
Yes. Yeah.
There was another paper that I came across by the group that proposed like a model called MEM. It's also a model editing, but the reason they use rank 1 matrix is because they say it's more computation efficient, but in this case, it's just because it's solution.
Yeah. Yeah, exactly. So that will be one baseline we want to compare to. Yeah. Okay. Actually, I think I don't have much time left, but yeah, I think the first paper is the most important one, because if you look at the second and third paper, both of them spend maybe 1/3 of their space talking about what's wrong and everything causal tracing in the first paper. So we will just finish the first paper and maybe go through the second and third more quickly. Okay. So, okay, up to this point, we already know how should we make the edit to have this W0 to become W1, so you can include this K star and the V star into your computation, into your model. The final problem we need to figure out is that what are they, right? I just told you how to put this into W, but you don't know yet what are they.
But there are so many W, which W we're going to edit?
So that's the question asked by the third paper. For this moment, we're just editing. Yeah, first of all, we're just editing after the first subject token. Second of all, the author just picked one early state. In particular, they picked the layer 6. In principle, you can pick different layers, depends on the causal tracing result, but they didn't want to run causal tracing for every single example. And they found that just picking layer 6 gives you good result.
Okay, so it's like from attacker's perspective, they want to edit the LM slightly, such that they want to achieve the answer as desired.
You can see that's attacker perspective. You can also see I correct some error that's in the original LM. Or it's like maybe some information is outdated, right? Maybe every 4 or 8 years, the president of US will change. If you don't want to retrain your model, you can do this sort of correction. Yeah. But attacker perspective is also very interesting perspective. Okay, so the final thing we need to figure out is that what is K star and what is V star, right? So here, K star is that you just average values over a set of text ending with the subject. In this case, it's like saying, if my subject is the Space Needle, I just have some random text related to Space Needle and have Space Needle at the end, right? I collect a set of them, and then I do this forward pass of my GPT, and I get the K star. Right? So if you like to read formulas, this is the formula, but yeah, it's actually just this sentence stating here, right? You take some other text, put it in front of your subject, and then you average all this together. So what is V? V is actually a little bit more complicated because it requires you to solve an optimization problem to get it. So basically it's saying that here I'm changing this single MLP in the middle of my network. But what I really care about is that at the last, I want to output Paris. So I want to optimize the output vector here, which is my V star. I want to optimize in a way such that the final output is Paris, right? So the way to think about it is that if I have a big neural network and I have this specific vector, I want to change it whatever as I like. Can I change it in a way such that it outputs Paris? It is definitely possible because you can imagine if your subject is not Space Needle, but say it's the Eiffel Tower. If your input is the Eiffel Tower is in downtown, then your output will be very likely to be Paris, right? You just need to figure out the representation at this specific place when you input the Eiffel Tower, then the output will be Paris. But in this case, we are not saying correspond to some specific input like Eiffel Tower. Rather, we're solving an optimization problem to optimize this vector here, right? Again, if you like to read formulas, the formula will be like this, but it's exactly what's showing on the figure here. The final step is to measure whether the edit succeeded or not, right? So here, we want to consider a few different metrics. The first metric is what we call efficacy. This is trying to show, just to answer the question, well, by doing the edit, did you change it to what you want or not, right? The second thing is what they call generalization. This is like related to the difference between relation and the prompt. If you rephrase your relation in different words, well, the edit still work. The third thing is what they call specificity. It's saying that if I want to edit something about Space Needle, I don't want my edit to change some other facts, right? I only want to edit this single fact. So giving you an example is that efficacy corresponds to, did I actually change Seattle to Paris? Generalization corresponds to, well, if I say it's located in here, instead of saying in downtown, well, I still be able to output Seattle. Specificity says, if I ask something about Pike's Palace, which is another place in Seattle, will it be affected or not? So here, they collect this data set with over 20,000 examples. And for these examples, they will be like something like the Space Needle is located in Paris. So the goal of the editing method is to insert this fact into the model, right? Such that when you ask things about Space Needle, the result will change. And to test the rephrase, like the generalization, there are some other sentences in the data set state the same thing in different ways. And to test the specificity, there are other questions asking, say, Pike's Palace and Boeing's headquarters, all in Seattle, but they don't want these places to be affected. And then the final thing is something beyond what we just talked about, but I think is more interesting, is saying that now I'm not going to ask something about where Space Needle is located, but I'm going to implicitly asking something about Space Needle. So if you correctly change the Space Needle's location to Paris, when I ask these kind of questions, you should answer me something about Paris instead of Seattle. So think about it. It's like you changed this fact. Later on, when you input this prompt into the model says, oh, here is Space Needle. So the model will first map the Space Needle to Paris and then output something related to Paris. So that's a way to test whether your edit succeeded or not. So for the baseline, okay, because of time, let me skip the baselines maybe. So we'll just look at the results here. So we talk about three things to measure, right? The efficacy, generalization, and the specificity. The authors, they propose different metrics to measure these three things. For efficacy, they propose two things. One is the portion of your input, your edited output versus the correct output. Or you can measure the probability change instead of the portion, right? Both represent whether you succeeded or not. And you can measure whether this holds through paraphrase. So you have two more scores corresponding to the generalization. Similarly, you can change the subject to your some neighbor subject. So you have this specificity. And finally, they take the harmonic mean of all three of them, which is the first score here.
I fear it's very hard to not interfere with other facts.
For one edit, it's not that hard. But if you try to change several things simultaneously, it's hard. Yeah.
Okay.
So here, these are the two other metrics they try to measure, which I didn't emphasize in the metric page. But what they are saying is that I want to measure the entropy of my generated text. This is like saying, I want the model still be able to something that's human understandable, right? Instead of something like not like natural language. The second thing is, according to the last row of the data set table, I want to have something in this case after the edit related to the O star, right? In this case, this will be Space Needle, this will be Paris. It's like saying after the edit, I will compare something generated about Space Needle to see whether that's consistent with Paris, some text related to Paris that I collected before. Again, so yeah, let's skip this part, but they actually have a like loss function to optimizing for these two metrics as well. So here is just a one quantitative example. I think maybe you can read about it on your own afterwards. A quick summary is that what this paper did is that they located the knowledge through causal tracing, and they added the knowledge through this rank 1 model update, and they measured the change using this counterfacts dataset. In particular, they proposed 5 different metrics. I think I only have 3 minutes left. So
I would just introduce the main problem, like what they want to do, and they kind of skip the methodology.
okay, so for the second paper, what they want to do is that they want to edit many facts at once, just like what's showing here. The challenge is exactly like you mentioned. These edits, they will interfere each other. So basically, the second one is more like an engineering work, right? So it's not like proposing some new methodology. It's the same author as the wrong paper. So they basically just saying that 2 things. One is that instead of having 1 K star and 1 V star, I want to batch a lot of things together as a chunk and update them at once. The second thing is that instead of multiplying 1 MLP, because now I have many facts, I want to modify a bunch of MLP so that for these hundreds of facts, they can still be edited, right? So I will skip the methodology part. You can come and talk to me if you are interested. Okay. But the summary of the second paper is that they try to do this edits of many facts, and then they just change 2 things from wrong. One is that batch-wise the processing. One is that modify many MLP layers. And then they achieve better specificity and efficiency. Okay. The third paper is actually also easy to summarize. So because the third paper basically makes one observation and challenges the setting of the wrong paper. So this is also why I think this is a really good open direction to explore, because many things are unsure now, right? So this is a NeurIPS 2023 paper. I actually got a chance to talk to the author at NeurIPS, and I find this super interesting. So from the title, you can already tell what's the key message here. They're asking, does localization inform editing? Like the 2 things proposed by Ron, right? They found something surprising, saying that the localization and the editing, they are not always consistent. So what do we mean by that, right? It's like if you first apply causal tracing to figure out where the knowledge is stored, and then you decide where to edit the language model to change that knowledge. These 2 places doesn't need to be the same place. In other words, if you think you have a good understanding of the model mechanistic, but it doesn't mean you can do a better control of the model. This paper actually just do a whole bunch of experiments and makes these 2 observations. They didn't provide a solution, but asked more questions regarding this. So every single one of those can be an open research direction.
Yeah, you see, ask the correct question can also make it a spotlight paper.
Right,
Yeah.
yeah.
Mhm.
So, okay, so maybe we just look at this page for this
Is
paper,
the third paper citing the like following up the previous 2, or it's like in
following up the previous 2, yeah. So basically, this is the figure we have already seen for the MLP editing, right? So what the authors did here is that take this matrix, takes the column-wise max, right? So because they are trying to compare the importance across different layers, so they don't care about the token dimension, they just take the max of each column. So what they observe is actually a histogram, like here showing in black. So, but they look back to both the Ron paper, the first paper, the Mehmet paper, the second paper we skipped. They both try to only edit this area, which is not consistent with the histogram discovered by this third paper. And they actually show a plot like this. So if you believe causal tracing is the important signal, and you use causal tracing to figure out where the knowledge is stored, right? But on the other hand, you test whether the writing will be succeeded, right? It doesn't actually matter what causal tracing tells you. If causal tracing says, oh, here is not important at all, but you edit it, you can still change the fact. If causal tracing says, here is very important, you edit it, you can still achieve the fact, right? So basically, it's like saying, if you want to rewrite something, you measure it. It doesn't matter what's the causal tracing effect. You expect to get something like super correlated in the red line, but this is what we observe. So they did a bunch of experiments under different cases, observed similar things. They fit a linear model saying that just give me the layer number, don't give me the causal tracing effect. I can do as much as giving me both. So they tested other problems instead of just inserting new knowledge, but like try to maximize the noise or erase some fact, amplify some fact, like 5 variant problems, the same conclusion holds.
Yeah, so I have to go, so probably like if
Okay.
people do not have time constraints, then can stay, but it's a very great presentation.
I
really like your passionate about this. Yeah, it's
Okay.
very good. Yeah.
Okay, thank you. So if
Probably,
people want to stay, I should probably be able to finish in 5 minutes.
Okay,
Okay.
great.
Yeah, and I will have the recording uploaded.
Okay.
So basically, now we get to the final part of the third paper. It's like where they propose new questions. So they are asking that, well, whether causal tracing is telling us anything meaningful, right? So yes, the answer is yes. Causal tracing is telling us the important part comes from the last subject token, right? So if we look back, what this paper did is that they took the max over columns. They ignored the difference between each rows, right? So that's because they find that indeed useful information was provided by causal tracing about the rows. They are just saying column-wise, causal tracing is not doing something right. So that's the first contribution they confirmed by causal tracing. The second thing is that they found that, well, editing earlier layers is indeed better if you edit here. But if you edit the later layers, well, it's not as good as the early layers. For example, here they tested the layer 28. For all the previous layers, it's kind of, you always succeed when you do the editing, but once you get to number 28, you basically never succeeded. Oh, okay. The next question is that, this is indeed a question they didn't provide any answer, is saying that if we validate the localization with editing, that's probably not the right way, right? They already verify the inconsistency between these two. So what should be the right way to verify the localization result? The third thing is that if these two different procedures are answering different questions, what exactly are the questions they are answering? Okay, so that basically finished the third paper. Finally, I want to talk about some future research directions that some of them comes from this paper, some of them comes from myself. The first thing is regarding the ROM paper. One thing is that they basically did all of their analysis about the MLP layers, but they didn't do much analysis about the attention layers. Maybe there is something interesting going on there. The second thing is that in terms of model fluency, right, ROM is actually not as good as some of the baselines. You can change the effect in the model more efficiently using ROM, but after this change, your model won't be able to produce results like with the same quality as the original GPT or with the same quality as the baseline edited GPT. The third thing is that they always framed their effect in this tuple version with subject relation object. But if you change your object and subject and state the same effect in a different way, the model will get confused. For example, you can ask, Bill Gates founded Microsoft. But if you change it, you ask, Microsoft was founded by whom? Then editing of the first cannot guarantee success for the second. some even broader applications, including like the third paper asked, what are the right questions to distinguish these two things? And also, this is asked by the second paper. If we are able to update many facts at once, will that make the interpretable models better than the opaque models? And the third thing is that, like Yiju's earlier question, can we add something beyond the factual knowledge, right? Not just tuple, but something more complicated. Will us be able to insert that into the model? The final thing is that figuring out how to correctly locate the fact is definitely going to lead to some better alignment method. All right, here are all the references for the papers I talk about today. Thank you for listening, and please come talk to me if you have any questions. I guess it's already over time. I will directly stop Zoom. For people on Zoom, if you also want to discuss these papers or the general idea, come to me offline. Thank you, everyone.